Welcome everyone. I am incredibly excited to guide you through today's explainer. We are taking a really deep dive into the fascinating world of digital signal processing. Specifically, we're going to demystify an absolute powerhouse of computing, the architecture of the TMS320C5x digital signal processor. Now, instead of just looking at this as a cold piece of silicon, I want you to imagine it as a highly specialized, ultra-efficient factory. Literally, every single component we're going to look at today has a very specific job on the assembly line, all working together to ensure absolute maximum throughput. Let's get into it.
So, here's the roadmap for our factory tour today. We'll start with the modified Harvard blueprint, look inside the CPU engine, explore its parallel processing power, break down memory speed versus flexibility, and finally look at connecting to the outside world.
All right, let's kick things off with Section 1, the modified Harvard blueprint.
Take a look at this. It's basically the complete architectural floor plan of our factory. As you can see, it is divided up into some very distinct areas. You've got the CPU down at the bottom, the memory blocks sitting up at the top, and the peripherals over on the right. But I really want you to pay attention to those thick, dark lines running horizontally right through the middle. Those are our critical data and program buses.
Now, what is so brilliant about this setup is how it solves a massive bottleneck. You see, while standard, traditional processors use a single highway for both instructions and data, which, as you can guess, causes huge traffic jams, the C5X uses what's called a modified Harvard architecture. It completely separates the program and data buses. It effectively gives our factory two entirely independent highways. That means it can fetch a new instruction and access the data it needs simultaneously, in one single clock cycle.
In fact, to actually make this work seamlessly, there are 4 parallel highways running through this chip. The program bus and the program address bus handle the instruction side of things, delivering the code itself and the addresses for that code. Meanwhile, the data read bus and the data read address bus are totally 100% dedicated to moving the actual data. Having these 4 buses allows the processor to grab an instruction and read an operand at the exact same moment without any collisions. It really is a logistical masterpiece.
Let's transition down into Section 2, inside the CPU engine.
Okay, so inside the CPU itself, the workload is divided up incredibly cleverly. On one side, we have the Central Arithmetic Logic Unit, or CALU. This is your heavy lifter, right? It does all the intense 2's complement arithmetic and packs a powerful 16 by 16 multiplier, a 32-bit ALU, and an accumulator. But sitting right next to it, operating at the exact same time, is the Parallel Logic Unit, the PLU. The PLU handles precise Boolean operations and bit manipulation. It can go in and directly edit data in memory without ever interrupting or disturbing the heavy mathematical work happening over in the CALU's accumulator.
So here is the absolute crucial point, the heartbeat of this whole thing, the MAC operation, multiply and accumulate. Because of the CALU's dedicated hardware, the C5X can multiply 2 numbers together and add the result to the accumulator in one single clock cycle. It's the digital equivalent of patting your head and rubbing your belly at lightning speed. This single cycle capability is the true secret sauce that makes this chip absolutely perfect for high-speed signal filtering, like instantly cleaning up the audio on a cell phone call.
And this perfectly illustrates the crazy depth of parallel processing here. Think about it. While the CALU is busy sweating over that heavy math, who is figuring out where the next piece of data actually lives in memory? Well, that's the job of the Auxiliary Register Arithmetic Unit, or ARAU. It manages all the addressing logistics, stuff like indirect addressing, block moves, and auto increments, utilizing its 8 auxiliary registers. Because the ARAU handles all the address tracking, the CALU is 100% free to just focus on pure, uninterrupted math.
Which brings us nicely to Section 3, Parallel Processing Power. To manage all this concurrent execution without losing its mind, the program controller relies on a 4D pipeline. You can think of this as an overlapping assembly line. Step 1 is fetching the instruction. Step 2 is decoding it. Step 3 is reading the operand, and Step 4 is executing and writing the result. What's absolutely amazing here is how these steps overlap. The CPU ingeniously reads data for one instruction on the 3rd stage while simultaneously writing data for a previous instruction on the 4th stage. It is just relentless efficiency.
Now, you might be wondering, what happens when an urgent task pops up? An interrupt. Does the whole pipeline crash? Nope, the system doesn't panic at all. Thanks to automatic context saving, it has a 1-level deep hardware shadow register stack that instantly, and I mean instantly, saves 11 critical CPU registers. The processor steps away,
handles the urgent task, and then drops right back into the pipeline exactly where it left off.
The program controller also maintains the critical status flags. Think of these as the control panel warning lights for our factory. You've got the overflow flag for when the math gets a little too big for the ALU. The interrupt mode bit, which globally enables or masks those interruptions we just talked about. The test/control bit to store logic results for branching. And finally, a very special one called the CNF bit, which actually configures our on-chip RAM. And actually, that perfectly segues into our next topic.
Let's dive into Section 4, Memory, Speed versus Flexibility.
So, the C5X utilizes two distinct types of RAM, and understanding the trade-off here is absolutely essential. On the left, we have dual access RAM, or DRAM. This is your ultra-fast staging area. It lets the CPU read and write in the exact same machine cycle, which perfectly feeds that 4-deep pipeline we just covered. On the right, we have single access RAM, or SARAM. SARAM offers way greater flexibility because it can be mapped to both program and data space at the same time. But it comes at the cost of speed. Multiple accesses here require one full cycle per operation.
Okay, remember that CNF dashboard light I mentioned a minute ago? Here is where it comes into play. The DRAM has a total capacity of 1,056 words, but the software engineer can physically reconfigure the layout of this warehouse on the fly. Just by flipping that one CNF bit, you can either have the entire 1,056 words act as data memory, or you can split it, turning a 512-word chunk, called block B0, into lightning-fast program memory. It gives you total adaptability.
Oh, and before we move on from memory warehouses, we definitely have to talk about security. The C5X features on-chip memory protection. This acts exactly like the factory's internal security system. By setting a maskable option, you can completely block any externally originating instructions from accessing the on-chip memory. It's basically like putting a VIP bouncer in front of your most sensitive blueprints, protecting your proprietary custom code from external snooping when the device is deployed in the real world.
And that brings us to our final section, Section 5, Connecting to the World.
You see, all that internal speed doesn't mean much if the chip can't talk to the outside world. That is handled by the on-chip peripherals. Think of these as our highly efficient loading docks. We have a clock generator with a phase-locked loop that can literally multiply the external clock speed to drive the CPU even faster. We've got a hardware timer, software programmable wait state generators that allow our super-fast DSP to patiently communicate with slower off-chip memory without needing extra hardware, and massive 64K parallel I/O ports.
Now, to handle serial communications, the processor offers a couple of highly specialized ports. For sheer, raw speed, the buffered serial port features an auto buffer unit. This allows for high-speed, continuous data transfer, which massively reduces the amount of times the CPU gets interrupted. On the flip side, the TDM, or Time Division Multiplexed Serial Port, is highly configurable for multiplexed operations. This makes it absolutely ideal for environments where multiple processors need to talk to each other over the exact same lines.
And speaking of teamwork and multiprocessor environments, some versions of this chip feature an HPI, or Host Port Interface. This is an 8-bit parallel port that lets a master host processor directly read and write to the DSP's shared memory. It essentially allows our high-performance DSP factory to act as a brilliant, incredibly fast coworker to a much larger host computer system.
So, as we wrap up our tour of the TMS320C5x architecture today, I want to leave you with a thought. Look around you. How do the devices you rely on every single day, from the smartphone in your pocket seamlessly filtering out background noise, to your car's complex audio system, how do they utilize the very parallel processing principles pioneered by architectures like the one we explored today? Next time you make a crystal clear phone call in a crowded, noisy room, remember the overlapping pipelines and parallel math engines working relentlessly in the background to make it happen. Thank you so much for joining me on this explainer, and keep learning.